Okay, today we're going to look at section 7.4, which covers logarithmic equations and inequalities. So a logarithmic equation is just an equation that has a logarithm in it. First, we're going to look at two examples that have only one logarithm in it. The first one on the left, we see we have log base 36 of x equals 3 over 2. We want to get this into exponential form, b to the y equals x, which in this case is going to be 36 to the 3/2 power equals x. Now that 36 we can rewrite as 6 squared. Replacing 36 with 6 squared allows us to cancel out those 2's, so we're left with 6 to the 3rd power. And of course, 6 to the 3rd power is 216, so x equals 216. In the second example, we have log base 16 of x equals 5/2. Again, we want to put it in exponential form, b to the y equals x. So we have 16 to the 5/2 power equals x. We can rewrite 16 as 4 squared and substitute that into our exponential form equation. When we substitute 16 for 4 squared, we can cancel out the 2's, which gives us 4 to the 5th power equals x. When we simplify that, we get 1024 equals x. In other cases, we could have two logarithmic equations, so one on either side of the equal sign, and this is going to require us to use the property of equality for logarithms. So what that property says is if b is a positive number other than 1, then log base b of x equals log base b of y, if and only if x equals y. So in other words, if we have two logarithms with the same base, we can set the arguments equal to each other. So if log base 5 of x equals log base 5 of 8, then we know 8 must equal x. So let's look at this example and use the property of equality. We know that we can solve this equation because we have the same base on either side of the equal sign. It doesn't matter what that base is as long as it's the same on both sides. So we can now set x squared minus 4 equal to 3x and solve. We bring the 3x to the other side, which gives us x squared minus 3x minus 4. And this is a quadratic equation. We can solve a quadratic equation in two ways. The first way is factoring, and the second way is by the quadratic formula. I know we did other ways, but these are the two that we're going to use the most, so just keep these in mind. And this particular equation can actually be solved by factoring, so that'll be a lot quicker. So when we're factoring, remember we're looking for two numbers that multiply to give us -4 and add to give us negative 3. In this case, those numbers are negative 4 and positive 1. So x is equal to 4 and negative 1 after we set both of those terms equal to 0. This is really important. For these types of problems, we must check our answers. The problem is not complete until we have checked both answers that we get. So first, I'm going to plug 4 back in for x. We have log base 2 of 4 squared minus 4 equals log base 2 of 12. Simplifying on the left-hand side, we get log base 2 of 12, and that is equal to log base 2 of 12. So x equals 4 is a solution. When we plug in negative 1, we get log base 2 of 1 minus 4 equals log base 2 of negative 3. Log base 2 of negative 3 is equal to log base 2 of negative 3, but we have an issue. Remember that your domain for the logarithmic function must be greater than 0. So because we have a negative 3 in the parentheses, that means that this answer is not valid, so x equals negative 1 is an extraneous solution. Let's look at another example. Log base 9 equals log base 9 of x squared minus 4x equals log base 9 of 3x minus 10. We have a base of 9 on both sides, so we can set x squared minus 4x equal to 3x minus 10. We want to bring the 3x over to the other side. We get x squared minus 7x equals negative 10. And then we want to bring the 10 over so that we can set this equal to 0. We get x squared minus 7x plus 10 equals 0. And again, this is a quadratic equation. We can also solve this one by factoring. So we're looking for two numbers that multiply to give us positive 10 and add to give us negative 7. And those two numbers are negative 5 and negative 2. So x is equal to 5 and 2. Don't forget to check the answers. So when we plug in 5, we get log base 9 of 25 minus 20 equals log base 9 of 15 minus 10. When we simplify that, we get log base 9 of 5 equals log base 9 of 5. So x equals 5 is a solution. When we plug in 2, we get log base 9 of 4 minus 8 equals log base 9 of 6 minus 10. On both sides of the equal sign, we get log base 9 of negative 4. And while these are equal to each other, again, our domain cannot be negative, so x equals 2 is an extraneous solution. Let's take a look at inequalities. We also have two properties for these. The first one, if b is greater than 1, x is greater than 0, and log base b of x is greater than y, then x is greater than b to the y. So this is not as complicated as it looks. If you see that example, we have log base 3 of x is greater than 4. Then when we put that into exponential form, we get x is greater than 3 to the 4th, and x is greater than 81. So it works just the same as equalities. The second property we have, if b is greater than 1, then log base b of x is greater than log base b of y, if and only if x is greater than y. And this also applies for less than. So let's look at an example. Remember, it's important to note that the domain of the log function is x is greater than 0. So in other words, you cannot have an x value that is less than 0. Because x cannot be less than 0, we want to set both of our arguments greater than 0 and solve for those x values. So we're going to take the first one, x plus 3, and set that greater than 0. When we solve for x, we get x is greater than negative 3. We can't do anything with this yet, so we're going to move on to step 2. For step 2, we want to take the other argument and set that greater than 0 as well. So 2x plus 1 is greater than 0. And when we solve for x, we get x is greater than negative 1/2. And for our third step, we want to solve the inequality like we normally would. So x plus 3 is greater than 2x plus 1, and we'll solve for x. When we bring over the x, we get 3 is greater than x plus 1. And then we want to bring over the 1, we get 2 is greater than x. Or in other words, x is less than 2. So we want to put all of these sets on the same number line because the area where all three of them overlap will be our solution set. First, I'm going to graph x is less than 2. Make sure you have an open circle. Next, we'll graph x is greater than negative 1/2, also an open circle. And then we'll graph x is greater than negative 3, again with an open circle. And this little portion in the middle where all three of our lines overlap is going to be our solution set. Putting that in set notation, we have negative 1/2 to 2. And here's the whole problem if you need to see it again. Let's do another example. Now remember, just like equalities or equations, this only works if you have the same base on either side of your equal sign or inequality sign. So for the first step, we're going to set 12x plus 5 greater than 0. And we get x is greater than negative 5 over 12. For the second step, we're setting 8x plus 9 greater than 0. And we get x is greater than negative 9 over 8. And then we want to set both of our arguments equal to each other, or less than or equal to each other. So 12x plus 5 is less than or equal to 8x plus 9, and we are solving for x. Bring over the 8x, we get 4x plus 5 is less than or equal to 9. And then bringing over the 5, we get 4x is less than or equal to 4. So x is less than or equal to 1. Now we're going to put all three sets on the same number line. Okay, now that all three sets are on the number line, we're going to take the part where they all three overlap, and that is our solution set. So we'll have an open circle at negative 5/12 and a closed circle at 1.